Alright, the topic of this video today is going to be combination of functions. So let's start off first. Let's define two functions. Let f of x equal 2x plus 5 and g of x equal the square root of x minus 7. And so we're basically going to look at two ways of combining functions. One of them is through arithmetic operations, so addition, subtraction, multiplication, and division. And honestly, this isn't that hard. It's just the notation. So for instance, if I want to add f of x plus g of x, obviously I could just write it like that, and it's not that hard. But another way that you'll often see it is f plus g of x. And so both of those are exactly the same thing. They're interchangeable notations, and it's exactly what you would think. You take you take f and you add g, and in this case it doesn't simplify anymore. That's your answer. And that's really all there is to it. So then if I want to do subtraction, it's the same. We just change that addition to a minus. Same thing with the other notation. I could write it like this. So I could say f of x minus g of x or f minus g of x. Either way, but it's still going to be the same kind of thing over here. We're just subtracting the functions. And if we want to multiply them, I could write f of x times g of x, or I could write fg of x. And in this case, remember, we're multiplying all of f by all of g. Just don't forget to put f in parentheses to show that the whole thing is going to get multiplied. Because if you don't have the parentheses, only the 5 is getting multiplied. And I shouldn't do that. You're not actually going to distribute across here because that's a square root. So this is as far as you can go. You can distribute the square root to each of these terms, but wouldn't do that. And then finally, I bet you know what I'm going to write next. It's going to be f of x over g of x, which is the same thing as writing f over g of x, which is f of x over g of x. And so there you go. Now let's just talk about domain really quickly. So the domain isn't that hard either, but if we were going to write, let's actually just find the domains first of all. The domain of f of x. So take a look at f of x. What are all the possible input values for x in f of x? And if you're thinking, can't x be anything? You would be right. So the domain, is that x is in the set of real numbers. And then the range of f of x, too many f's. I'm actually going to move this down. Let's make some room for ourselves. So the range of f of x, and again, actually, you know what? We don't even need the range. I'm not going to bother. But by the way, in case you were wondering, because this is a line, a diagonal line, the range is going to be all real numbers. But let's look at the domain of g of x. So if we take a look here, it's a even root, so we do have to keep the radicand non-negative, which means x minus 7 is greater than or equal to 0, or x is greater than or equal to positive 7. So let's kind of keep that in our minds. And the only thing about arithmetic operations and domains is this. So the domain of any arithmetic combination of f and g is the domain of f and the domain of g. It almost sounds redundant. Sometimes you'll hear it said, referred to as the intersection of the domains, but we're looking for values that are in both domains. And there's one little special case where we have to put a little extra, and that's going to be our division case, because we also have that special case since g is now in the denominator. We know that denominators can never be 0. So I'm just going to put a little note here. Note. Remember, denominators cannot equal 0. Okay, so how is this actually all playing? So let's take a look now at these functions. So we have our domain. Our domains of f and g are listed up here. And so what's the intersection of these two sets? In other words, what do they have in common? Well, if we're looking for numbers that are all real numbers and greater than or equal to -7 or to +7, numbers that are real and greater than or equal to 7 are just numbers that are greater than or equal to 7. So the domain for this first one is x is greater than or equal to 7. Same thing here. Domain is x is greater than or equal to 7. Next one, domain x is greater than or equal to 7. Now, we do have a little special thing here. Because denominators cannot equal 0, in this case, x can also not be 7. So, in this case, we're going to say x is strictly greater than 7. We're not going to put the equal to on there. But that's pretty much all there is to the first kind of ways of combining functions. When we talk about arithmetic combinations, we're talking about addition, subtraction, multiplication, and division. And so that's pretty much all there is to that. Let's take a look at just a couple of things you can do with this, and then we'll move on to the other way of combining functions together. So let's talk about evaluating. So again, I'm just going to go ahead and keep using these. Let's let f of x, since it scrolled off the screen, let's put it here to remind ourselves. And g of x equals the square root of x minus 7. So one thing that you might have to do with these is evaluate them. So let's look at how you can evaluate them. And there's kind of two ways you can do it, and really it's a toss-up of which way is faster. I don't think there's a difference between them. You're doing the same stuff, just in slightly different orders. So let's say that this was our problem. We want to find f plus g of 11. Now, like I said, it's really doing the same thing. You're just doing things in slightly different orders. So method 1 would be to find f of 11 and g of 11 first, and then add the results. Or another way you could do it, so method 2 is actually find the function, find f plus g of x first, and then substitute x equals 11. And like I said, it won't matter. You're going to find you're doing the same stuff, just slightly different order. So let's do method 1 first, because that was method 1. So we find f of 11, which is 2 times 11 plus 5, which is 22 plus 5, so it's going to be 27. And then you find g of 11, which is the square root of 11 minus 7, which is the square root of 4, so that's 2. So then f plus g of 11 must be 27 plus 2, so it's 29. And there's our answer. Or we can find f plus g of x first, which in this case is just 2x plus 5 plus the square root of x minus 7. And so that means that f plus g of 11 is 2 times 11 plus 5 plus the square root of 11 minus 7, which is 22 plus 5 plus 2. Oh, look at that, which is 29. And you can see how we were, excuse me, how we were really doing the same exact thing, just in a slightly different order. So some people like it this way. You're kind of breaking things up. You're breaking a bigger thing up into smaller chunks. Some people like to get it all over with at once. Really kind of a personal preference. So that's one thing you can do with them. And let's look at what you can do with them as far as graphs go. Okay, so let's look at this one. And let's say that the problem said to graph f minus g of x on the same set of axes. Well, I can't spell. So what is that talking about? Well, think about what we did up on this previous problem. Whoop. Remember how on this previous problem, when we wanted to find f plus g of 11, we found f of 11 and then g of 11 and added them together? So we added the output values together to get the final output. It's the same kind of thing here, except this time we're going to be subtracting the output values. And remember, the output values are the y values. So this problem is really focused on the y values. So what you do is, like right here, we have these 2 points that are lined up. They have the same x input. So let's make sure we get order right, because remember, order matters. So we're going to do f minus g, which in this case is green minus orange. The green value is at -2. The orange value is at 0, so -2 minus 0 is -2. So I'm going to start off right there at -2. Then we have another set of points that are lined up on top of each other. And again, f minus g is green minus orange. So -1 minus -3 is -1 plus 3. So that's 2. So now we're up here. And then we do it again. Now we have another set of points that are lined up. Green minus orange is -1 minus -2, which is -1 plus 2, which is 1. Whoops, but not right there. Over here. And then finally, green minus orange, 2 minus -2 is 2 plus 2, which is 4. So the purple ends up being y equals f minus g of x. So again, what we did, we wanted to find f minus g, which is green minus orange, but we're focusing on the output values. We're focusing on the y values. So green minus orange. Sorry about my dog. -2 minus 0 is -2. -1 minus -3 is 2. -1 minus -2 is 1. And 2 minus -2 is 4. And that's how I got those points. That's another thing you can do with them. So that is arithmetic combinations of functions. So now let's look at the other one. What is that? So the other way to combine them gets a little funkier, but it's not too bad, but just is a little, it's not quite as intuitive. But it's called composition of functions. So first I'm going to give you the notation, and then I'll show you what it actually means. So there's actually 2 ways to write this, like there were 2 ways to write the other way. So you can either write it like this, where it's f of g of x. And notice we're placing g inside of f. and I have an extra parenthesis here. There we go. That looks much better. So we're placing G inside of F. So that's one way of writing it. Another way of writing it is you'll see it like this. And some people call it the fog notation because it kind of looks like you're writing fog, except that's not a 0 or that's not an O. It's an open dot. Think of a degree symbol, but it's just written lower than we typically write a degree symbol, but it's about that size. Maybe slightly bigger, but when you're handwriting, it doesn't really matter. But make it smaller. Don't make it full size like an O. It really is a small open circle. And there's different ways of reading this. You can really read either one, either way, but just the way that they're written, you'll hear a lot of people read the first one as F of G of X, because that's exactly how it's written. And then a lot of people read the second way as F composed with G. And then sometimes they even put the of X at the end. But really, I mean, you could read either one either way and it would be totally acceptable. But there's just two ways of reading it and two ways of writing it. But what does it actually mean? So let's just go back to our good old f of x and g of x that we've been using on this. So we had f of x was 2x plus 5, and g of x is, what was it, square root of x minus 7. So let's find, I'll make this part A. Let's find f of g of x. So it means exactly what it says. Remember function notation, whatever's inside of the parentheses, that's what you substitute into the function. But this time inside of the f parentheses is g of x. So that's what we're going to do. We're going to take f of x, but we're going to substitute in g. And so that means that in the function f, wherever there was an x, we're going to put root x minus 7. So it's going to be 2 square root x minus 7. And that is f of g of x. And voila. That's all there is to it. So if we went the other way, if I ask you to find g of f of x, can you find that? Go ahead and pause the video and try it and see what you get. Alright, so when you substitute in, the first thing you're going to replace f of x with what it is. And then you're going to put 2x plus 5 into the g function. So it's going to be the square root of 2x plus 5 minus 7. And that's g of f of x. Now in this case we can simplify it just slightly, because I can simplify what's inside and say 2x minus 2. And voila. We're done. So that's composition. That's really, I mean, that's composition. Now there's a little more that's information about them, but that's really the idea of it. So let's first look at evaluating them. So let's say you had this example. Let's say we want to find f composed with g of 23. Now just like we had two different ways of doing it before, we're going to have two ways of doing it here. And I'm going to say if, and I'm going to go ahead and use the same ones we had above. And g of x is the square root of x minus 7. Okay, so let's see what happens. So, method 1, you can find f composed with g of x first, and then substitute x equals 23. Now we already found f composed with g, because remember we did that up above. F composed with g, that was part A. Remember, this notation is the same as this notation, so we already found it right there. So let's just make use of that. That is 2 square root x minus 7 plus 5. And that makes sense, because again, this means put g into f, so we're going to put this expression in place of x, which is exactly what we have there. And then we plug in the 23. It's pretty straightforward. So f composed with g of 23 is 2 times the square root of 23 minus 7 plus 5, which is 2 times the square root of 16 plus 5, which is 2 times 4 plus 5, which is going to be 13. So f composed with g of 23 is 13. And voila, we have that. Well, what's this other method? So start with the inside function, and we call them inside and outside functions. It's a little more clear in this notation. G is inside of f when we write it this way. If I look at part B, this time f is the inside function and g is the outside function. In this problem, it's always the outside is the second one, so it's inside, outside. G is the inside function. So you start with g. Actually, I'll say evaluate the inside function at x equals 23, and then plug the result into the outside function. And that makes a lot of sense. I'll show you what I mean. So the inside function we said was g of x, and g of x is the square root of x minus 7. So we're going to replace the x with 23. And we get square root of 16, so we get 4. And then we take that output value and we put it into f. So we're going to find f of 4, and we get 2 times 4 plus 5, which is 13. And it's the same thing we got on the left-hand side. So f composed with g of 23, what a shocker, still 13. But here's why that makes sense. I'm just going to do a little thing over here. Remember another way to write f composed with g of 23. Another way to, another way to write this part right here is f of g of 23. And we just found g of 23. G of 23 was 4 because we plugged in the 23 into g. But then the output of g becomes the input of f. We put 4 into f. And then that gave us 13. So that's why method 2 works and makes so much sense, because that's exactly what the composition notation is saying. So basically, again, kind of recapping here, when you're evaluating compositions of functions, you can do it one of two ways. You can either first find the composition and then substitute in, or you can evaluate the inside function, and then that output becomes the input for the outside function. So there's a little more about compositions that we're going to talk about. Let's look at domains of compositions, because it gets a little different now with domains. All right. Domains of compositions of functions. Now there's this crazy way of describing the domains with words, but it's very confusing sounding. Don't think of it that way. I'm not even going to put it down here. I'm not even going to read it. You can look in the book if you're really curious. Let's just look at a couple of examples about domains. So now I'm going to switch things up a little bit. Let's say that f of x is the square root of x and g of x is x squared. Now hopefully you guys can look at this and go, oh yeah, I know that the domain for f is x is greater than or equal to 0, because x can't be negative. But over on g, we don't have any restrictions on x. We can do anything we want. So x is all real numbers for the domain. That doesn't matter. Let's look at both ways of composing. Let's look at f composed with g and g composed with f and see what happens. So A, find f composed with g of x and its domain. So now I'm going to put the domain part in there. And then let's look at B, which is to find g composed with f of x and its domain. All right, so let's go ahead and do it. Let's just find the compositions first. So f composed with g of x, that's where we're going to put g into f. So it becomes this. This expression for g goes into f, and we wind up with this. But make your math teacher happy, and hopefully you remember that the square root of x squared is not just an x, it is the absolute value of x. And then in part B, if we find g of f of x, so this time we're going to put f into g. So this goes inside there. So we have the square root on the inside and the squared on the outside. And we wind up with this. When you do it this way, you don't need the absolute value. So let's take a look then. What is our domain for both of these? I mean, obviously the functions are different. But if we look at just the result, just the result here, well, it looks like we can take the absolute value of any number. There's no restrictions. It looks like we should have all real numbers. And then over here, it's just x. X can be any number, so it kind of looks like these would be all real numbers on both of them. I mean, if you think about the graph for the absolute value, whoops, remember the absolute value one, that's the one that just looks like this. This is really the identity. That's the one that just looks like that. Except that's not really what we've got. Why not? Well, this is where, honestly, the best way, I think, to find the domain is show every little step going along and make sure you're making note of any restrictions on x. So, for instance, this first thing right here, I have a square root, and we know we have restrictions when we have square roots. The restrictions are that whatever's inside has to be non-negative. So if I think about that, that means whatever is inside has to be greater than or equal to 0. But wait a minute. Think about that. It's being squared. If you square any number, you're going to get a positive number or 0. You're already greater than or equal to 0. So that actually is all real numbers. And then on the next step, what we wrote, there's also no restrictions. So actually, the domain, because we ended up with no restrictions, even though it seemed like we were going to, we had an even root, so you set the radicand greater than or equal to 0, but it turns out all real numbers can satisfy this equation, so it's all real numbers. And there's no other restrictions that show up, so it's all real numbers. So the domain here is x exists in the set of real numbers. Let's look at part B. Now, even though a lot of you could probably go, oh, I'm just going to do the square root and square, they're going to cancel out, I'm just going to go to x. Don't do that. Again, like I said, when you're doing compositions, show every single step so you can look for those restrictions. So in this first step, we're taking the square root of x first. And the square root of x, it's an even root, so whatever's inside must be greater than or equal to 0. And there's no way to simplify that down. Like this simplified down to all real numbers. This doesn't simplify. And here we didn't have any further restrictions to add to it. So over here, our domain is that x is greater than or equal to 0. And it makes sense when you think about it. I mean, some of you guys can already see that it makes sense the way it's written right now, but remember, this part A, f of g of x, says to evaluate g first and then put it into f. If you plug any number into g, as soon as you square it, you're positive or 0. So when you go to x, or when you go to f, if you plug in any positive number or 0, you're okay. There's no restrictions, so all real numbers. But on part B, it says to start with f. F is the square root of x. So in order to start here, we have to make sure that x is non-negative. But then we get an output that can go into g. Any number can go into g. So we have to say that x has to be non-negative because we're starting with f. Let's try another one. Let's say that f is the square root of x minus 7, and g of x is x squared. So go ahead and try it on your own if you want. Same directions after that. So find f of g of x and its domain. And then find g of f of x and its domain. So pause the video and give that a shot. Alright, so here are the answers. So let's take a look at them. Very similar to the problem up above, but that little minus 7 makes them a tiny bit more complicated. So when we're doing part A, f of g of x. So g is the inside function. So we're going to take g and put it inside of f. So it ends up looking like this. Now we do have an even root. So remember, whatever is inside the root, the radicand, must be non-negative. Must be greater than or equal to 0. So if I start solving for x, I wind up with this compound inequality. And then that's it. I can't simplify this anymore, so that's pretty much my answer. I've got it. So f of g of x is this. And for the domain, I just wanted to show you, I could have written it like this with the inequality. It's a little awkward the way I have it, though. For a final answer, we usually start with the smaller number first. If you do interval notation, though, the intervals have to go in order from the left to the right on the x-axis. So I have to start with this interval and then wind up with this interval. But that's it. So then if we look at the other way, this time I'm going to put f inside of g. So I'm going to take this radical and put it inside of g. So it ends up looking like this. So before I simplify anything, I have the square root. So again, whatever's inside has to be non-negative. And I can simplify this. The square root and square can cancel out. And I should have had absolute value symbols, and I didn't. Shame on me. But I have that, and then I say that x is greater than 7, greater than or equal to 7, because that was here. And so then I pretty much have it. And then that's it. Yeah. So that's compositions. Let's look at one last thing, which really isn't that bad, and it's backwards. How about decomposing functions? Decompositions. So here's a problem on decomposition of functions. So how does this work? Okay. Like I said, we're going backwards. It's basically giving you the answer. After you composed the functions, you got this. So what could you have started with? So find an f and a g such that h is g of f of x. This is h of x, and we want h to be g of f. Remember, always think about inside functions and outside functions. And there is definitely an inside function. And so if you take a look, this 2x squared minus 3 is inside the cubed. So our inside function should be f of x. F of x is 2x squared minus 3. And our outside function is the cubed, but you just have to say x. X is kind of your placeholder in the outside function. And that's really it. Now every year we give these problems, and some students are very creative and they find all these crazy ways to do it that do legitimately work. Keep it simple, because honestly, the reason why we do this, there's a form of derivatives in calculus, and actually integration too, where you deal with inside or compositions of functions. You want to keep it simple. Look at the inside and look at the outside. Don't try to find some crazy value for f, like 2x minus 7 to the power of 2/3, and if you plug it in, then I just made that up. It's not going to work. Don't be creative. This is one time I don't want you to be creative. Keep it simple, because that's the skill that's going to help you next year in calculus. So I'll give you a couple more, and then you can try these on your own, and then I'll put up the answers. But they don't get really any more complicated than this. All right, so here's two last problems for you guys to try. Again, look for the inside functions and outside functions, and I'll reveal the answers in a moment. So pause the video. All right, so here we go. If we take a look at the first example, this expression was inside an exponent. So let's make that our inside function. Then replacing that with the placeholder of x, our outside function is 5 to the x. Second example, this expression of 5x minus 3 is inside the denominator. So let's make f of x equal 5x minus 3. And when we replace that with a placeholder of x, we get the outside function is 1 over x. There you go. So there's combinations of functions in about a 40-minute nutshell. All right, have fun, and I'll see you in class.